Welcome to another tutor short provided by the Educational Support Services Department of Lehigh-Carbon Community College in Snexville, Pennsylvania, which is just outside of Allentown. These videos review key learnings for the science courses provided here at L-Tri-C. And please remember that the Educational Support Services Department does provide walk-in tutoring 5 days a week. This video is an introduction into vectors and how you can add and subtract vectors. When you think about a car traveling on a road, it's very common for us to say the car is doing 50 miles per hour. That is a scalar quantity. In this case, it's speed. The car is traveling at 50 miles per hour. We're only talking about the magnitude of the speed. And examples of other scalar quantities are temperature, mass, and time. However, for a vector, we could also say this car is traveling at 50 miles per hour, but it's heading in a direction. It's going due east. Once we add the direction to the scalar quantity, we now have a vector. A vector has both magnitude and direction. So velocity, momentum, and force that we'll deal with in physics are vector quantities. So we're dealing with direction, not just the quantity or magnitude. Now, if your vectors that you're trying to add or subtract are in the same line, essentially parallel vectors, then addition and subtraction is very straightforward. As an example here, we have a plane. The first part, we're saying the plane is traveling at 100 miles per hour. So we're over here. It's traveling at 100 miles per hour due north. And there's a tailwind that's also heading due north at 20 miles per hour. So those vectors will add, because they're in the same direction, be simply 100 miles an hour is due north, plus that tailwind helping it at 20 miles per hour, also north. You end up with an overall speed of 120 miles per hour going due north. Conversely, though, if that headwind or that tailwind had actually been a headwind, so that it'd be working against, in this case we see down here, now it's working against the direction of the airplane, it would subtract. And you can look at this as the plane is traveling 100 miles per hour north, but the headwind is now 20 miles per hour south. And recognizing that south is opposite to north, you would subtract and get 80 miles per hour north. Or you can do it this way, where you have your 100 miles per hour north for your airplane, and just put in that your headwind is actually minus 20 miles per hour north, because it's heading in the opposite direction. And you still get your 80 miles per hour north as your overall vector. So when vectors are parallel, it's very easy to just add and subtract. But they're not always going to be parallel, and often in your physics classes they won't be. And so there's a couple of ways to look at vectors that are not parallel when you go about adding and subtracting. So one method here we call the Parallelogram Method is if we have two vectors. Here's vector A going to this direction, and we have a vector B going up this way. Well, you can draw a parallelogram that we show here with the dotted lines and the two vectors. And when you add A and B together as vectors, your resultant is this R, this line here in the middle. So by drawing a parallelogram, you can calculate what this resultant vector will be using normally either use graphing or trigonometry. But you draw the parallelogram and then solve the problem that way. In a similar fashion, an extension sort of this parallelogram method is a triangle method, where again you have this A and B quantity, and as we said before, we draw this parallelogram. But that's essentially the same as taking this B and putting it on the other side of the parallelogram. And you can think about this as being someone who walked this distance and then at this point went up to B, and now you have your resultant, which is still the diagonal in the parallelogram. But now you're sort of set up more with a triangle, and you go about using trigonometry or graphing in order to solve for this resultant, which is the hypotenuse of the triangle. Now, what we find is graphing, as we've been saying, graphing or trigonometry. Graphing is a cumbersome way to solve these problems. You don't want to be graphing every problem you have and taking out rulers and trying to calculate distances. So the trigonometry is really the way to solve these. And that the use of that trigonometry is going off that triangle method. And when you use trigonometry, you call it the component method. Get up here. So you're going to start, if you think about here, you have a vector. It's at some angle theta, and it has a magnitude, or the scalar quantity of A. So you can define this vector A as having a magnitude of A and a direction of theta. Well, using the triangle method over here, you can consider this vector A as having two components, one in the x direction and one in the y direction. And so we represent them with this sub x and a sub y on the a's. And again, as I mentioned, the triangle method, using this angle, depending on what properties you know, you can solve for the other properties. And if we look back down here to look more at the trigonometry involved, AY over here, if you notice, it's on the opposite side of the angle theta, which in trigonometry is represented by the sine function. So if we know the magnitude of A, you take that magnitude times the sine of theta, that'll give you your magnitude of AY. And similarly, get the magnitude of AX, you would take the overall magnitude A and do it times the cosine of theta, cosine being adjacent to the theta. And remember, for sine is opposite the component that's opposite of the theta angle. As I said, in your problems, you may not know A, but you may know what AX is. And from that, knowing the angle, you can solve for A. So you're going to get all different types of situations where you'll get some information and you'll have to figure out the rest. So using this component method, the hypotenuse A, using Pythagoras theorem, you take the squares of either side of this right triangle and then take the square root and you can get your magnitude of A. The other property you can use is for theta, is the tangent of theta is going to be opposite over adjacent, or AY over AX. So if you become familiar with your trigonometry and the functions involved, you will use them often throughout this whole course of physics for resolving vector quantities. Let's use an example here to go over a component method problem. So let's suppose that we walk 433 meters east and then walk 250 meters north. And we're looking for the resulting vector for the displacement of our trip. And remember, displacement is the difference between the starting point of our trip and the ending point. And it doesn't regard the path. So this length r, the vector r, is going to have a magnitude or a length. It's going to be less than the walking we did, the 433 and the 250, because as far as the vector is concerned, we did it as the crow flies, not as how we walked. So since we know sort of the x component here and the y component, we can get the magnitude of that vector r by using Pythagoras' theorem here. And from working that out, you'll see that your magnitude of your vector r is 500 meters. To get the angle, theta, which is right here, we're going to use trigonometry. We use this function here. The tangent of theta is y over x, or 250 over 433. And you'll see that that will give you an angle of 30 degrees. So the answer for the displacement vector for this trip, you would say this is the vector r, which is 500 meters in a direction 30 degrees north of east, or you can say 30 degrees from the x-axis. And because it's positive, it'd be up this way 30 degrees. As we said, you do have to be careful as you're representing angles. Make sure you have the sign right and that you reference off of which axis that the angle is being determined from. So that's an example of a simple component problem. But you can extend the component. Often you'll have more than one vector, of course, and you're trying to add these vectors together. And again, we're saying here they're non-parallel. And so just looking at it, if you again have a one vector v1, which is here in red, and then a vector v2 over here, and this v2 could have been coming off at this point. In physics, you may be working on a free body like a car, and it has two different forces on it. But using that triangle method, you're going to translate this this vector here over to up here in order to form your triangles so that you can resolve the mathematics involved in these problems. So we're trying to find the resultant vector here when you add up these two vectors. And you can break each vector. If we look at the red vector here, v1, it has a x component along here and then a y component here. And when you look at your v2, you have an x component and another y component. And so you can get the overall x component of the entire resultant, this v vector here. You can get the x component by just adding this one and this one here, as we show here. And you can get the y component adding the y directions together and get the y component. And then once you have y and x for the overall vector, you can solve for v. And once you have that, you can also get the angle because you have the two sides of the right triangle. So that's what you're going to do for addition of multiple vectors, and it can get pretty complicated, but if you work your way through in one direction at a time, often do the x direction, then the y direction, and work your way through it, you should be able to do it. It just does get tedious. So let's take an example here of a component analysis where we're adding two vectors together. In this case, we're saying we have a mail truck that first drives 22 kilometers due north from the post office, and then he drives in a direction of 60 degrees south of east for 47 kilometers. And we're looking for the overall displacement from the post office. So the overall displacement, here we are. First we drive our northerly direction, then our 60 degree in the south of east direction. What we're looking for, the resultant, would be right here. So this is the resultant we're looking for. I'm going to call it V in this case. But that's what we're trying to solve for. What was the overall displacement vector? So when we look at the first step in our trip, our A, because it was directly north, doesn't have any direction or any distance in the x direction, or in this case east. This is your x direction. But it does go 22 kilometers in your y direction. So for vector A, because it was in the direction of our axis, wasn't too hard to calculate the components for. However, when we get to vector B, we're now dealing with an angle other than the x or y axis. So when we look at angle B, let me get my blue pen here. When we're looking at B in the x direction, this is your 60-degree angle. So B is going to be in your x direction, which is adjacent to the 60 degrees. So in trigonometry, you're going to use your cosine function to resolve that component down. So B in the x direction, we know we traveled 47 kilometers in B, but that x component is going to be factored by the cosine of 60. So you end up actually in the x direction only going 23.5 kilometers. So we have 23.5 going this way. Then this is your B. The y component is going to be opposite to 60 degrees, so you're going to use your sine function. And very important, it's going to be negative. You are going opposite than the positive direction in y. So it's important to put a negative sign in here. Again, your 47 for your overall, we know this hypotenuse is 47 meters, but times sine is 60. So we know we're doing minus, this component down here is minus 40.7 kilometers. So we have our components for B. Now we will just add our components together. So for our overall vector V, Vx, the sum of the x directions, Ax plus Bx, is going to be 0 into 23.5, or a positive 23.5, which makes sense. If you look over here, it is in the positive x direction. When we look at our green resultant here. Now, our y direction overall should be negative, and we'll look, we have our AY is AY up here is your 22 kilometers, and then your BY over here is your minus 40.7. So together you get your minus 18.7 kilometers. Therefore, now that you have your sides of your vector here, V, you can use the Pythagoras theorem and you get your overall magnitude of V, just 30 kilometers. And the direction, and you're going to take for your tangent of theta, you're going to take your y over your x. And remember, it's negative, and you're going to end up at a minus 38 degrees. So let me see if I can show you here. This is going to be, this angle, theta, is minus 38.5 degrees. And the magnitude of V here is 30 kilometers. So you could say V, your vector here, it's a little hard for me to bold it like I have up in the text. So I'll put this line over it to say that's a vector. We would represent this as 30 kilometers, I would say, in a direction of minus 38.5 degrees from x-axis would be a resolution for that. So I know I went through this fairly fast, but you'll be doing a lot of this in your physics courses, and you do need to be proficient in doing this type of trigonomic analysis as you work through all the problems you're going to be dealing with. Thank you.